Okay, we're going to do some more applications with exponential functions. We're going to work mainly with growth and decay here, which are biological or chemical applications. So the formula we're going to work with mainly here is a of t equals little a times b raised to the t. So in this case, the little a is a starting amount. The b is an exponential rate in decimal form, as we'll see that in a moment. And t is time. Okay? And in this case, since b is an exponential rate, depending on the size of b, if it's bigger than 1, that means we're increasing, and that's growth because that's more than 100%. If the rate is less than 1, that means it's decreasing or decay because that is a portion of something, like 75% would be 0.75, that's less than 1. Okay, so if you're given a function, you should have the b in some cases, and in some cases you'll actually have to make the b. But let's see how we're going to use this formula in a couple of examples. Okay, so the first example I have here is Dr. Ray has a culture of 50 mold spores. This particular mold is known to grow at a rate of 8% per day. Write a function that will calculate the number of spores present after t days and determine the number of spores present after 3 weeks. So let's kind of figure out a few things here. So in our idea of a of t equals a times bt, we need two things. We need an a and we need a t. An a and a b. My t got messy. Boop, boop, boop. Okay, so we need an a and we need a b. Well, the little a is the starting amount, and it looks like we're starting with 50. Okay, we have 50 mold spores. Now the b is a little bit more complicated in this in here, because it says we're growing at a rate of 8% per day. Now that is very confusing the first time you see it. But if I was to put over here in this b position 8% or 0.08, that would just make things get smaller. I would be taking 8% of whatever I had. So what we're going to do here is, if it's growing at a rate of 8%, we're going to start with 1 because that's the original amount, and we're going to add 0.08. So the b will be 1.08, and that's from 100% plus 8% would be 108%. So that's the exponential growth rate. So we're going to use 1.08 in our function. So we have a starting amount of 50, and we're adding 8% each time, which means we're keeping the original 100%, which is 1. So our rate will be 1.08. So the function will look like a of t equals 50 times 1.08 to the t. Okay, now that's the function. Now if we want to do it for 3 weeks, let's see, t equals 3 weeks. Well, it's very important to notice that this thing says that the growth rate is per day. So 3 weeks is 21 days. So let's see, a of 21 would equal 50 times 1.08 to the 21. So let's use Mr. Calculator here and see what we get. Depending on what we want to round it off to, I'm just going to go with 252. I got 251.69 and so on, but we'll say 252. Okay. Let's go to the next problem. Next example here. Should be the same idea. So it says a 500-gallon pool is left unattended over the summer. The water in the pool evaporates at a rate of 10% per week. Write a function that shows the number of gallons left in the pool after t weeks. Okay, and again, how much is left after 3 weeks, but everything is in terms of weeks. So let's see here. Our function, or our template for our function, is a of t equals little a times b to t. So we need little a and we need b. So we need a, which is our starting amount. That is the 500 gallons of water or whatever is in the pool. Now it says we're evaporating at a rate of 10% per week. So when we say B, we're not going to use 10% again. We're going to use basically the 100% is what we have, and we're taking away 10%, which means we're really keeping 90%. So we might be decreasing it by 10%, but that means we're keeping 90%. So if we think about that the other way, 1 minus 0.1, 90% is the same thing as 0.9. So that's what I want for my B. Okay, it's evaporating, so the amount of water is decreasing, so it's going to be keeping 90% of the water if we lose 10%. Okay, so let's see here. Our function will be A of t equals 500 times 0.9 to the t. And if you like parentheses around that, you can. But that's our function, and then it says after 3 weeks, so t equals 3 weeks. And it's important that they said this rate of decreasing at 10% was per week. So we only need to plug in 3. We don't need to change it to days. So context is very important in these problems. So 500 times 0.9 to the 3. Calculator is beside me, and you can test your theories about how good your rate is based on whether or not you get a number that's appropriate. So if I started with 500 and I messed this up, I'll know I messed it up if I get a number bigger than 500, but I get 364.5, which will be gallons, left after 3 weeks. So that is definitely less than 500, which is what I would expect if water is leaving the tank, or the pool, sorry. Okay. Let's do another problem. I think I got 2 more here. So this is a half-life problem. We're still going to use the same formula, but it says the half-life of a substance is the amount of time it takes for a starting amount to decay to half of that amount. When working with exponential decay, the half-life can be used to write a function. Okay, so it might help us get some things that we might not have. Okay, so let me try and slide this down a little bit. Okay, so the half-life of a particular substance that decays exponentially is 125 years. Use this information to write a function that will calculate the amount of a 75 kilogram sample left after t years. So half-life, what does that mean? Well, we know that we have the exponential function model, a of t equals a times b to the t. Now we can use this 75 to start with, but we don't have to. But basically what it's saying is that if we start with 75 for the a, we might not know the rate, but we know after 125 years for the t that we should be left with half of 75. So half of 75 is 37.5. So we have everything in the equation except for the b. So let's kind of solve for the b. So I can divide both sides by the 75. So I'll have 1/2 or 0.5 equals b to the 125. Okay. So what can I do here? I need the base. So you might be thinking of a logarithm, but I need the base. The logarithm would be helpful if I wanted to find the exponent. But we got b to the 125. We could take the 125th root. And if we do that to both sides, we'll isolate the b. So b will be approximately, and if you take 0.5 and take the 125th root of it, you can expect to get something very close to 1. Let's keep a couple decimal places here. 0.9945. Because these things are going to be so close to 1 when you take heavy roots of them that it might be bad to round too far. But the function would look like this. A of t for the ending amount equals 75 for the starting amount times 0.9945 to the t. So basically we know this is decay because the rate here, the b, is less than 1. Okay, So it didn't ask us to calculate any particular future value, but knowing the half-life can let us set up the function, and then we can actually figure out how much is left from any amount. So if I wanted to go 5 years, 500 years, I can now plug that in for t because I know how the actual substance decays. I have a rate for it. Okay. Let's see here. Let's do another one. A lab creates a new molecular compound that decays at a rate of 12% per hour. What is the half-life of the compound? Okay, so we're given different information here. We're asked to find the half-life. So again, we're with A of t equals A times B to the t. So we can start off with any amount we want. There is a 30 number here, so let's just use that. A is 30, and we can write a B because it says it decays at a rate of 12%. So we can say 1 minus 0.12. So the B would be 0.88. Now that's a rate, that's not a time. Okay, so when we set up the function, it can look like A of t equals 30 times 0.88 to the t. So if we plug a number in for t, we will know how much is left after that amount of time. But we don't know the half-life time. But we do know that 15 is half of 30. So we can plug that in as an ending amount and figure out the time that would work there. So now we have 1/2 equals 0.88 raised to the t, and this time we are looking for an exponent. So we can change it to a logarithm. So log base 0.88 of 0.5 equals t, and that looks like a good change of base formula. Log of 0.5 over log of 0.88 equals t, which, let's see what that gives me. Log of 0.5 divided by log of 0.88 gives me t to be 5.42, and we were talking about hours, so hours. And that is our half-life. Okay. So we found the half-life. Now, that's really irrelevant to the question that's asked over here. It says how much of the 30-gram sample is left after 6 hours. So these are two completely different questions that you don't need one for the other. But we can come back and we can say A of 6 equals 30 times 0.88 to the 6. So let's see. It should be less than 15, right? Because at 5.5 hours, we should have half of the 30 left. So if we go to 6 hours, there should be less than half of the 30, so less than 15. So let's see here. I'm going to do some calculating. I get that after 6 hours, we have 13.93 what we got here, milligrams left. And that's after 6 hours. But we were given information about how it changed, so we could actually find the half-life. So if we want to know when to go back and there'd only be half of it left, we know that's around this 5.4 hours. All right, good stuff.